we made this clear, and all of you apparently were okay with that one. Let's forget about everything else. Now, this is not the problem. Please, everybody listen. Rather than looking at your note, listen to me to understand what mistake you made, that you don't have to come back again to me. So I put here 50 pound-foot of torque here. Yes or no? What do you think the torque inside here is? 50. Yeah. What would be the torque here? First of all, 50 goes this way, action-wise. Yes or no? Then here, what would be the torque? 200 minus 50. Everybody knows that. Yes or no? And then here, how much torque will be here? Still 200 minus 50. Yes or no? Which is this one? Is that correct? That's 200 minus 50. Is that correct or not? Yes. So this should be 150. Correct? So why, as soon as you change that to TB, what was it, the question there? TB, and you change that to TA, what difference does it make? Yes? Still is the same thing. First of all, there are people doing all odd sort of thing. I don't know. Many people, they said phi of that one equal to phi of that one, which is correct if you want to do, because phi of the, any part you cut it, phi of the left must be equal to phi of the right. Why you are cutting there? You can do that, but you don't remember. Here the torque is how much? Let's put it back there. Now, the biggest mistake that everybody makes, and maybe that's why you don't understand that, you are mixing the external with internal. I have made a note for many of you. I ran out of red ink, by the way, because this is what you are doing. You want to express the torque in the shaft. This is the shaft B, or what was it? B, D, C, A. Is that correct? The torque here is related to that. Many people, in order to that, first of all, this is external, this is external. There is a big difference between TB and TBD. Everybody understand what I'm saying that? And since you're making that mistake, you can never get this one correctly corrected. TB is different from TB. TB actually is the external torque applied on the gear there. Is that understood that? There is a TB here. However, let's assume this is the problem. If I want to calculate torque here, if I have one here, another one here, I have to add up. This is torque BD. This is torque at B. B is external. This is internal. Everybody understand that? This is the key for the other problem. Now, saying all of that, obviously many of you wanted to say the total phi must be equal to 0. Yes. Or you can say three things. You can say that phi of D with respect to A must be equal and opposite of phi, because when we go opposite, you go to the other. So with respect to phi of the B with respect to D, something like that. Is that correct? Or D with respect to D. But therefore, or you can put total phi equal to 0. Since many of you use this way, so I'm going to that. The total phi must be equal to 0. So let's start from here. Correct? What's the torque here? You said 50. The torque here is how much? The torque in the body here will be equal to TB. Everybody understand that? Therefore, that I have TB times L. What is the L there? L is, look at the picture there. L is 12. That's right. Divided by G and J are the same for all of them, or they are different? They are. One of them is, yeah, this one is smaller. Yes or no? So let's calculate that one. G is the same. So the J, you all calculated that correctly. The J is equal to G is equal, this is G, and the J is 0.0981. So if in inch to the power of 4. But is it going clockwise or is it going counterclockwise? Remember, you are going action, action, action. That is going to be going clockwise. Therefore, it is negative. Then you go to the second part. The second part is how much? You already gave me the answer. Will be 200 minus TB, which is TA. Is that correct? See, that's the whole thing. 200 minus TB is equal to TA. And many of you written that down. Because when you look at the static of this one, remember that TA plus TB is equal to 200. Now you can exchange it, write it any way you want to. So therefore here is TA. Everybody understand that. But it is going this way and that way. Is that because this is the reaction, this is the action. But I'm starting like as usual here. This goes clockwise. This goes clockwise. This way going to go counterclockwise. The other one is going to go counterclockwise, looking at this way. Some of you start from that side. That's okay too. So, but you have to be sure about the sign. Everybody understand that. So that one is 200 minus TB, or TA, whatever, some of you put TA there, which perfectly is okay. And that is the length of that one is 8 divided by G times 0.0981. And the last one is plus 200 minus TB or TA. So you can replace that any way you want to, times 5 divided by G times 6, I'm sorry, that one is 6.13 times 10 to the power of minus 3. And since this is equal to 0, G and G and G drops out. You can change that to T. Some of you wrote it like that, TA. This one will be 200 minus TA. In other words, it's two equation and two unknown any way you look at it. This is the sum equal to 0. You should use the same technique you use in homework number 1 and 2. The only difference is TA is unknown, and I don't understand you. Many of you wrote phi of that equal to phi of that, but as if this part doesn't exist even. How can it be? This is the 3-part shaft. Is that correct or not? Mistake. Many of you forgot. As you assume 200 is here, you put phi of this equal to phi of that. You put here TA, you put here TB, I don't know, all sorts of things. But look at your picture. Picture tells you what to do. Is that correct or not? Anyhow, making to a little bit smiling at least, it was so bad that at the end I add everybody 3 points. So if you are 20, getting 20, you are not 23. So smile. So I add 3 points to everyone. Because it was so bad, I didn't want you to leave it at that. This was the lowest score I got. Everybody getting that. So if you had 10, so your score actually is recorded 13. Is that understood? Across the board, I add 3 points to everybody. Because I don't know where the mistake is, but most of you, 80, 90% of you. Then you do some other odd things. As I said, you are looking for internal, not external. Everybody understand that. The internal, you have to call it TB. But that T, this T that I put there, actually TBD become equal to TB. Everybody understand in magnitude. Is that correct or not? Yes? Got it? Okay, so that's part A. So you calculate that one. So TA, the rest is very simple. So TA become equal to, or TB become actually, the way I did it was differently. This is you solve for TB, so TB become equal to 176 pound-foot, and TA become equal to 24 pound-foot after that. Or you can set up 2 equations. The rest is throwing. This rest is not that difficult. However, many mistakes. Tau equal to. Now here it is the mistake that I saw. I don't know how many times I have to explain that. I said, what is the unit of stress, guys? Let's review that, because there are at least 1/3 of people do not understand this unit of stress yet. They are or making mistake. What's the unit of stress? PSI, or did you ever see me using pound per foot square? Why do you changing the I to or J to the foot square? And I don't understand, or to foot to the power. By the way, if you find anywhere in the strength of material book, you find this, the unit of stress a pound per foot square, which at least 10 of you calculated that way. I give you A for this course and next course. Exactly like what I was saying before, as if you are mentioning the distance between here to San Francisco in 2,300,000,000 inches. It is 350 miles. Everybody gets the idea. Everybody understands that. As soon as you change that to pound per foot square, after 50 years working in this business, I don't understand what you are talking about. It's so unfamiliar to me. Everybody getting it? The unit is pound per, that SI. PSI means pound per square inch. Everybody understand. KSI means per square. We never, ever express that there. Now, what you do, you change when you are calculating stresses. Some of you did. Still look at your homework. You change the J to the foot to the power of 4 instead of changing this one, T. This is pound-foot. All you have to do, multiply that by 12. Everybody, are not the other way around. So tau, when you get that one, so let's say tau AB, which is the shear stress, AC, I'm sorry. So this is AC. So therefore, from here to here, which is equal to TA, TA ends up to be 24. So it is 24 times 12. Everybody understand that? That is pound-inch of force multiplied by J. J is 0.25 divided by, because it is quarter of an inch, divided by 6.13. Many people express this in foot to the power of 4, change to the foot, because they have not done their homework or they are not listening to me either way. So therefore, all you have to do, change your torque into system, and I did it many, many times. So that's 11,746 PSI, and so on and so forth, because the rest is very simple. Then tau CD is also equal to the same amount of torque, because remember, here internally this is equal to TA, internally equal to this is TA, internally this is equal to TB. Everybody understand? But don't forget, this and that are external. Everybody understand that? You are trying to find out the torque inside. This is the torque inside. So therefore, this one become also 24 times 12. This one is half an inch divided by 0.0981. Only I'm here, quite frankly, looking for unit, and many of you made mistake there. So, and finally, the last one, I put it here, tau dB is equal to 176 by multiplied 12 multiplied by 0.5 inch divided by 0.0981, or equal to 10,765 PSI. These are some of the highlight that nobody should make mistake as far as the PSI and KSI goes there. Then, of course, I calculate for part B. That's what part A. At part B, I calculated what is the rotation of the C with respect to B. Now, if you did the first part right, probably you would do the second part right. Many of you choose this part because that's what. But this phi is equal to CA as well. Yes or no? So you could use that one, or you can use this one. Which one is easier? CA, because the phi of this part and phi of this one must be equal and opposite. Everybody understand what I'm saying? That. However, if you are using this one, notice this one is going to go, because at the end, TB end up to be equal to 176. So this is 176 clockwise. This is 24 is counterclockwise. Everybody understand that? So the sign is different. Many of you calculated it correctly. They put the two together, but you use plus and plus. It's not plus and plus. One is plus, one is minus if you're going. But the other side is easier. Anyhow, in other words, use this two, use this one. Yeah, 8 inch, which was the 5 inch. Now, this one. So use this one versus this two. This is the answer, actually. Is that correct or not? Yes? Do you follow what I'm saying there? This is phi of AC. This is the phi of the other two. Is that correct or not? So that's the answer. You don't have to look there. Just you plug in the TB and you calculate that one. All of this being explained. Is that correct or not? And finally, the last one, which many people get it correctly because there was nothing to do with this. How many horsepower do we need to calculate, to create 200 pound-foot of the torque? Of course, remember, this is pound-foot. Again, you have to watch out the unit. Then you don't need to multiply it by 12. Why? Because this was the number of horsepower multiplied by 550. But 550 has a unit, pound-foot per second. Remember that? Therefore, this is pound-foot. This should stay pound-foot. Actually, if this is pound-inch you're calculating, you have to divide it by 12, or you multiply. If you are putting this in pound-inch, you have to make this multiplied by 12. I mentioned that. You have to match the unit. Many people do not even pay attention to the unit. I don't know how you do the homework, because these are all repeated in your homework. But, of course, many people got this part correctly. 2 pi, and for heaven's sake, if this is 1200 revolution per minute, revolution per second is not 1200 times 60, is that? That's a bad mistake. Correct? I had few people here and few people in the other class because they are not thinking. So 1200 divided by 60 become the revolution per second, must be much less. Is that correct or not? If some motor running at 1200 revolution per minute, each minute is 60 seconds, you have to divide, not multiply. Is that obvious? Yes or no? Correct? It's that bad sometimes it gets. A couple of people or few people multiply that by 60. Is that understood? Okay. Anyhow, the horsepower ends up to be equal to 45.67 or 0.7. Of course, you cannot find that in the market. You go by whatever is closer to that. This one. Anyhow, as I said, I add everybody 3 points. The rest of the homework here, I put it all here. So let's move on. That's your homework for next time. So that's chapter 5, which is the discussion today. But we are going to have a quiz this Thursday about chapter 4, which is the homework that you have already. Is that correct or not? So you want to see me during the office hour, all your questions, which will be all the stresses in chapter 4. Yes?
Is RPM given? Or are we just supposed to assume RPM?
I know I added on the board.
Oh, okay.
I put it on the board, 1200. I forgot to put it there, but I put it on the board, 1200. Not on the text, that was not there. Why I correct that. Also, I went and give it to the people that were taking it. I gave 1200, yes. I should have given it to you, of course. Without RPM, you cannot calculate that. Okay, now guys, we are going to get into a new territory. So I want you to understand that this is, at the same time, which is very, very easy, is one of the most misunderstood part of the lectures, ME 218, which you not even need it for all you mechanical engineering and civil engineering and aerospace engineering, manufacturing. You need this chapter 5 for the rest of your life. Without this chapter 5, you would never become an engineer. Let's put it this way. Everything that you do in future is about the civil engineering courses like 303, 304, 305, all related to the shear and moment diagram. I'm going to go a little bit, as usual, in the detail at the beginning, because everything is in the detail at the beginning, not later on an example. If you understand what I'm talking to you about today, everything becomes very simple. I have had a student, even today in ME 219, after 8 weeks of lecture, still do not understand the sign convention for a shear and moment diagram. So let's go through this in detail. You want to go to the next page of your note, start fresh. And right on top of your note, this is shear and moment diagram. And the first thing that you put there, it is internal, it is not external. ME 218, as I said it before, is all about internal, not external. That's one of the mistakes that people will make. So therefore, let's understand what we are talking about. We are talking about shear and moment diagram. Shear and moment diagram. Now, before I start on any of this material, I'm going to give you some explanation why do we need shear and moment diagram in a beam usually. Now, of course, shear is, we usually call it V, and the moment is M. And it is internal. Please write it down in front of that, internal, external. Let's say that we have a beam here. We start it like this. And I put here a load P. The load P, I can give it a number. That doesn't matter. Let's say 100 pounds or 1,000 pounds. That doesn't matter. It's a load P there. Everybody from static knows that we did that many times in chapter. This is such a simple case that if I make a cut here, there is internally in each beam, there is a shear and there is a moment. Remember chapter 1, the internal forces, and this is very simple. So if I cut there at the distance A, for example, so let's call this distance A. A will be given to you. So if there is a here, and you do a free body diagram of the beam there, there is a 100-pound force here, external. This is external. Now we are going in the body. Everybody does. And notice, every chapter we went through, it was about in the body, what's happening to the body of the rod or shear or bending, why it is bending, why it's going stretching. Delta was about the elongation of the rod. It's all about stresses inside the body or the deformation of the body, yes or no. Now, what should I have by static? This is very simple. By static, I should have here a force going like this is outside, this is inside. We call it shear force. Is that correct? Yes? Chapter 1, we saw that how we cut the stresses. Tau was equal to force over area. By the way, in chapter 6, we are going to change that altogether. Tau is not equal to shear over area for the beam, because beam has a large section. Chapter 6 is allocated to the shear and the stresses due to the shear. Is that understood? We are not talking about that. We are not talking about shear and moment diagram. Okay. Is this finished? Is this in equilibrium? No, of course, everybody should know that. If you know that, then you don't know your static, because this is a couple. Everybody see that this is a couple, and therefore it should be there a moment. Everybody knows that, so I'm going to assume. So the action is here. This is the first thing. The action is going to here. If you put it this way, it's wrong. Everybody understand that, because this system should be in equilibrium, so the action is going that way. The reaction should be like that. So this is the real one. I am not talking about sign convention, not yet. So if this is distance A, the shear should be equal to 100 pounds going up, and M should be equal to 100 times value of A, whatever that A is. Is that correct or not? Yes? And it should be clockwise. Is that correct or not? Yes? Now, of course, for this simple beam, if A changes, if I go from here to here to here, notice the value of the shear does not change, remain constant. Is that correct or not? But that's not always the case. I can change the load, put another load here, and another load here. When I come here, the value of shear also changes. Is that correct, everybody? For this beam, simple beam, the value of shear from the beginning to the end seems to be equal to 100. Is that correct? Because there is no other load for single. However, what about value of M? Is it constant or it keep changing? That will be dependent on value of A. Everybody, if you are in 1 here and epsilon here, the moment at that point must be equal to 0. As you go further and further and further, the value of M keep. So where do you think the M is maximum? At the end. This beam is very simple. So if you are a civil engineer or mechanical engineer, or you want to design this as a beam, where do you go to check your stresses? At the middle of the beam, beginning of the beam, or at the support? At the support. Is that understood what I'm saying? That? So therefore, this is a simple case. If I want to design this beam, because the moment here is P, let's say the length of this beam is 6 feet, the moment here is not P times A. The moment here is P times 6 feet, because it's the largest value of M. Everybody understand that? Yes? So therefore, since by inspection, I know here, first of all, and then which way this beam bends. Look at it. This is what chapter 4 was all about. If this beam bends like that, where is the tension? Where is the compression? The top is in tension. Here will be the tension. So if I'm checking my stresses, depend on the size of the cross section. That was chapter 4. That's what you are going to have a quiz. So please pay attention to all your, everything we do is like that. But the first thing we have to do now to determine where M is the highest value, yes or no? Otherwise, how can I design a beam? Because the design has the same section from beginning to the end. So I want to go where M is the highest value and where shear is the highest value. Everybody understand that? So this problem was very simple, but I immediately can change it to this problem. For this problem, it's obvious I have to go to the end. Is that correct? Because that's simple static. Force times this distance. Is that correct or not? Then you decide on the side, tension on the top, compression on the bottom. But look at this beam now. If I give you a beam like this, which is a simply supported beam, and then put a P here, P1, and P2 here, maybe a little load like that there. Everybody see what I'm talking about? See, as you can see, the shear value keep changing as well, is that the moment keep changing. So the idea is, if I have a beam like that and I want to design it, I have to go to the section which has the highest value of shear, and another section which has the highest value of moment. So the idea of shear and moment diagram is to find, so this is the, now after explanation of that, to find M max and V max in order to design it to find the stresses due to that. So if I make it safe at those spots, the entire beam then later becomes safe. Is that understood? Yes, how to find the highest value. In order to do that, we are going to call this M always as a function. This, first of all, we are going to call this X usually. We choose a center of coordinate. For this one, this will be X. This will be Y. This is center coordinate. So as you go forward, the value of X keep changing. So if I give you here, for example, 1 foot here, 2 feet there, 1 foot there, 1 foot there, half a foot here. So as you see, the value keep changing. I have a beam of 3, 4, 5.5 foot, and then I have to decide where the M is the highest value. Is that understood? So to do that, we plot shear and moment diagram. Is that understood? So that's the idea first, why we are doing that, but many people get confused about it. Then we get into the most difficult part of this chapter, which people do not pay attention, although it's very simple. 2 facts. I'm going to put it here and keep it here. Fact number 1 is the static sign convention. So please write that. For a static sign convention, so because I'm going to change that in a minute for this system, everybody thinks that I'm changing the static. No, the static remains the same. If you have a system of coordinate of this is X, this is Y, this is Z, which is the typical of what we use always, this never changes. So anytime you have a force going this way, that force is positive. Going that way is negative. The same thing here. The forces going up are positive. The forces going down are negative, and also the moment the same way. I'm putting everything in the positive direction. Counterclockwise is positive, clockwise is negative. And anytime you use static equilibrium, which is sigma fx equal to 0, sigma fy equal to, notice how much detail I'm giving you guys in order not to make the mistake, some of the mistake that everybody makes. If you go to ME 219 today in my class, and I give the problem like this, what you see there, still half of people do not get it right. Everybody has problem with the moment diagram. Somehow they get the shear diagram correct. Moment diagram, everybody has a problem with. And without the moment diagram, you cannot design anything. You cannot become a designer. Everybody understand of any part of any structure. Everybody understand it, yes? Now, what's the big deal? I'm going to introduce a new set of sign convention to you, which has nothing to do with the static. First of all, write it down. It is something to do with the deformation of the beam. The beam either deform like this or deform like that. Is that correct or not? Every beam that you loaded here, I erased it. You put here a load somewhere. Anyway, you see that? It goes down this way. Is that correct or not? This is the deformation we are talking about. Therefore, I want you to understand that anytime we have a beam, we are going to plot X versus the shear. The shear could be in pound or in kilonewton or newton. And we are going to have a diagram for the moment here, M. And notice, since these are variables, these keep changing, this curve may go positive or may go negative. Now, we have a sign convention for tension and compression. Do you recall that one, guys? If I put here a force, so I'm sure I made that clear here. This statically is positive, yes or no? Correct? But is it tension or compression? What? What did you say? Both? Yeah. Well, you gave correct answer. What did you say? Tension? I said this is a force. This force is statically is positive. Is it tension or compression? What would be your answer? Yeah, none, neither. That positive has nothing to do with the tension and compression. It is statically positive because it's going this way, and this is my axis. Is that correct? This is not either tension or compression. That depends. You are right. That's it. So look, if I put that force here, now this item becomes, but look, I need one force here, one going to the right. This is positive, this is negative. We are not talking about that. We are saying this is a compression, therefore it is negative. Everybody understand that? Therefore, we need two of them. Now about here is the same thing. If I want to draw, let's say my moment diagram becomes something like that, for just sake of it. We don't know yet how it's going to happen. This part is plus, this part is minus. And let's say my shear diagram by any chance end up like that. I don't care what I mean, later on we discuss how, but it has a plus side and a minus side. These are about stresses happening due to the shear and moment inside the body. Therefore, it should be either tension or compression, this and that. Is that understood? That? So therefore, we need a new sign convention. These are sign convention, write it down. For the shear and moment diagram, which is different from here, and it is something like this one. Is that correct? Here is that you have a piece of beam. Right now, this is not deformed. Yes or no? Now, if the beam looks like this is before deformation. If it ends up like that, this is now the new item you have. This is a smiley face. Yes or no? Okay, this is why I started this 25 years ago, so everybody knows that. This is why. Smiley face, when it behave like that, we are going to call it positive. Everybody. Now, to get it to that form, look, I need a negative moment there and a positive moment there. Everybody understand that, what I'm talking about. Therefore, it becomes like a tension and compression. This statically is negative. Everybody understand that. This statically is positive. But if the beam smiles at us, we are going to call it positive. So anytime that you are here, this beam there is smiling at you. Is that correct or not? What's the opposite to that? Is like that, which is frowning, which sometimes I call it before quiz, after quiz. Sorry for that. Sometimes, not always. Sometimes you are always smile after quiz too. Is that, especially for that quiz. That was bad, guys. I didn't expect it from you. You see, not after all the discussion we had and all the scenario that I explained to you, I expected much better result. Is that understood? Yes? So I give the 3 point because of degree of difficulty. Everybody understand that? Yes? However, don't make that. So therefore, here, if this moment is this way, it is frowning. Yes or no? So in other words, look at this. Is this beam frown at us or smile at us? Frown. So the moment here should be plus or minus. The moment here, oh, I didn't say that. But let's a smiley face, we are going to call it plus. Of course, the frowny face, we are going to call it minus, which requires this action. So again, one more time. This is going to be like that. Actually, this statically is positive. This is statically is negative, but the beam behave in the frowny format, so we call it negative format. Is that understood? Yes. This is all being in the handout as well, but you need to write. Okay. So that is as far as the moment is concerned. Notice we have the same thing to have it for the shear as well. Is that correct? Now for the shear, you have to look again at this picture. Look at this side is going like that. It's going down. And this side, it seems to be going. Just look at the slope of that. It's changing it. So for the shear, this is for M. So this is sign convention for M. Again, look at it. This should be statically positive. This should be static. In other words, when you draw a free body diagram, you want your M to be in the positive format. On the right-hand side, you put it like that. On the left-hand side, you put it like that. Everybody understand? Don't worry about the static. A static comes afterwards. Is that understood? Yes? And then this is for negative format. Now, for the shear, we do the same thing. So if the body is like this, let's say the beam is like this at the beginning. So let's say it ends up like that after deformation. But look at this part. This part originally was like that. Now it ends up like this. So what happened to that? This side was pushed down. this side was pushed up. Notice, again, statically this is negative. Statically this is positive. But this format, strangely enough, we are going to call it plus. Remember at the lecture 1, there was all the shear in the handout that I gave you. They were drawing it downward, and I said I will explain that to you later on. This is that later on. Because the shear is going downward on the right-hand side and going upward on the left-hand side, then we are going to call it plus. So if I'm looking at this beam, this side is plus, everybody, because this side is pulled down. So look at this one. However, this side is not the same. This side behaves totally opposite to that. So if the before the formation is like that, after the formation become like that, so this side goes up, look at it, and this side goes down. You need a pair here, like here. You need a pair. So therefore, this one we are going to call it negative, correct? Now, going back to some of the example I gave you, now I want you to just practice this a little bit before we go into the system. Here is a beam. I just show it to you. I can show it again. Somebody puts a load there. This beam goes like that. Is that correct or not? Is the moment should be plus or minus? Plus, because all smiley face. What about the shear? Plus or minus? Look, this side is plus, this side is minus. Ahead of time, you have some idea. If you really look at the sign convention, you get everything there. But look at the other beam that I showed you. This beam, when you put the beam here, is going to go like that. Is that correct or not? Is that correct or not? Is this moment should be plus or minus? Minus. It's a frowny face. Everybody see that. By the way, when you look at it, here is compression, here is tension. Reference to chapter 4. Is that correct or not? And this one is reversed. Tension is on the top, compression is on the bottom. As you see here, tension is on the top, compression is on the bottom. Therefore, it should be negative. How about the shear? The shear is going to be like that. What is happening? Is it plus or minus? Minus, because the right-hand side is up, the left-hand. Everybody see what I'm talking about? So there is all related that. Did you get that sign convention, which is explained in your handout there? Now I'm going to keep this here. We don't need this part. This is the most important part. You have to pay attention. Then there is another little table. I'm going to put it here later on, which relate this all together. Let's start doing a few simple example of shear and moment diagram. You put this simple example, understand what I'm doing, then the rest become very simple. It's just a combination. You just add it together. Is that correct? So let's look at that. So be careful of what you are doing and how you are handling this simple problem. The first problem I want to do is the following. Okay, this is a beam. Let's say it's a 6 feet long, that are just for the sake of number, but I can put here P or whatever in general. But let's say here is 100-pound force applied there. And I want you to draw the shear and moment diagram. I already explained it to you. I already saw what happened there. Is that correct? But let's do one more time for entire beam. Okay, so this is point A. This is point B. I don't need the reaction here because this is free. I can start from here. So this is what we do. Generally, always, you put X versus shear, and then you put the unit there. Don't forget the unit. The unit could be pound, or it could be kips, or could be kilonewton or newton. You put it there in order not to draw that. And then underneath that, usually we do all in the one batch. And underneath it, we do X versus M. Of course, M in this case will be pound-foot, because this is expressed in foot. Don't change that to inch. Is that understood? Yes? Notice all the pound-foot. I gave you a quiz was in pound-foot, but that was a torque. This is bending. Remember the difference between that problem, that was a torque scenario. This is a bending. Remember, you have to calculate the M, then go to chapter 4. Everybody understand what I'm? Chapter 4 was just the stresses due to the M. Is that understood? Yes? We did that. Some book, actually, they explain this first, then they calculate the stresses. There are different versions of that. Here, anyhow, how do you think the shear going to be? Let's assume you are going at a distance A in your head. This is what you should do. Make a little cut there. What's the shear value? Is it plus or minus? Is it 100? So just do the static in your head. This does not require a free body diagram. When things become a little bit more complex, which I'm going to do when I do a larger beam on Thursday, I'm going to draw for you the free body diagram. But this is such a simple case, does not require a free body diagram. If I make a cut here, this is down, the shear must be going up. Is that plus or minus? This is the first time. So that is minus. What's the value of that? 100. Does it change as I go forward? No. So therefore, start from here. You cut it here, 100, 100, 100, 100. Is that correct? So it is minus 100 all the way from beginning to the end. So it is a constant shear. Is that correct or not? It just happened to be constant. Not always this the case, though. Everybody understand that? Yes? Okay? What about the moment then? We already know a little bit of a static there, so it should help us. So what do you think the moment that here is? I already did it for you. The moment must be 100 times A. That's the magnitude of that. The only question is, was it plus? Was it is it like that or is it like that? Which one? Is that correct or not? Minus, yes or no? Why? Because people make mistake here. Why they make mistake here? Because they go by the action, not by the reaction. You see, the action of this force is 100 times A and it's going that way statically is positive. Yes or no? Is that what you want? This system has to be in equilibrium. Guys, see, this is a mistake that I just saw in one of you. If you have a 100 here, can I put here a moment like that? Is that correct or not? Both of them going in the same direction. Everybody see that? So here will be the reaction equal and remember what I just told you a minute ago, the mistake you said I'm getting all my M and I'm getting negative. I said because you are not calculating the reaction. You have to put sum equal to 0, by the way. So this is very simple. I'm not going to do that. Obviously, if the action is like that, the reaction should be like that, which makes it negative. So the moment must also be negative. However, is it constant or is it changing? Changing with the value of A. So at A is 0, the moment is 0. Then A become 1 inch or 2 inch or 1 foot. Just keep increasing. So that is the, where is the M max? We already know that. The M max is there where the distance becomes, and that's it. So this is minus 100 shear become, M become minus 100 times A or X, sometimes we call it, because I can change that to X. And if you want to, so it is linearly going that way, yes or no, correct? What's the value of maximum M, which is a negative M? That means it is like that. Everybody see what I'm talking about? And then what's the value of that? Of course, the value of that is minus 600. This is something you can do it with the static. These are pound-foot of moment, and this is the highest value we knew ahead of time, correct? Example 1, which is very simple, yes? Now let's go example 2. I'm going to do all of that in a series of them, and then putting it together will be very simple. Now this time, I'm going to put the same beam, but this time I'm going to put a this is the same 6 feet. This time, this is 100 pounds per foot. That's the intensity of that load. Is that correct? That's a uniformly distributed load from the beginning to the end. Of course, the total load is 600. Everybody see that, yes? Which you can put it at the middle to find the reaction. But we don't want the reaction. We want to draw shear and moment diagram. Everybody getting the idea here? This is, everybody knows that, or should know that this was lecture 1, homework number 1. 100 times 6 is 600. You put it at the centroid of that to find the reaction here and there. However, look what happened here. If I change this beam, don't draw it, don't write it down, to this format, these two are not going to behave the same. So you cannot change, write it down. For shear and moment diagram, you cannot replace a uniform load with a single load. You can do it to find a reaction or use it for a static, write it down clearly in your note. You can replace a uniform load with a single load to use the static for finding the reaction, but you cannot draw shear and last quiz, ME 219. 5 students did that out of 45. Still, they got the uniform load, they changed it to a single load and trying to draw the shear and moment diagram for much more complex problem. No, they forgot about this fact. Is that correct or not? You can do that for static purposes to calculate reaction. Here, you cannot, as you see, this problem and this problem behave totally differently. Everybody see what I'm talking about? Yes? Okay. Shear diagram. Now, this is the shear, again. Point A, point B. You bring those points down. Usually you put it A, B. Sometimes there are 10 of them, so don't worry. These are the simple problems. What's the value of the shear there? By the definition of 100 pounds per foot, if I'm at epsilon distance, how much load do I have? Epsilon times 100 is how much? Come on, guys, answer. Epsilon times 100 is how much? It's not 100 epsilon. It is epsilon is 0, yes or no? 100 times 0 is 0. So the shear starts at 0, although it's not like that. That was 100 there. So start at here 0, yes or no? Because if I'm here at the distance of 0, 100 pounds per 0 is 0. Is that correct or not? Yes? It's 100 pounds per foot, but I have 0 foot. Is that correct or not? Yes? Now, if I go 1 inch, 1 foot, how much do I have to go? How much shear do I have? 100. 2 foot? 3 foot? Therefore, the shear must be what? Linearly going down. And is it going, oh, I gave it up. Okay, I gave the answer. Going up or down? Because this is down, the shear is up. When it is up, look at it. When it is up, it is negative. Is that correct or not? Actually, it's in reverse. Remember that. Therefore, I must be going down. Okay, let's draw that straight. Okay, this is X, this is B. So it must be linear this time. What's the maximum shear now? The maximum shear will be 100 times 6, or it's minus 600, which is really the reaction here. Is that understood? Yes? Correct? Happy? Not smiling. You are not looking at the sign convention. Okay, look, all I'm saying that, draw a little free body diagram here. Let's say this is 1 foot. Yes or no? Correct? Well, how much load do you have here? 100 times 1 foot going down. So how much shear should I have here? 100 going up. Look at the sign. Is it this one? Is it looks like this one or looks like that one? Which one? Which is negative. So that's it. However, if I go to 2 feet, it becomes 200, 100, 200, 300, 400. Therefore, it must be linear. That's what. So now it's mine. Okay. Everybody get it? Yes? Now, how about the moment? Now, look at the moment. What happened to the moment diagram? For moment diagram, this time I'm going to draw a little free body diagram. So let's look at the free body diagram. Exactly what I draw here, I'm going to draw it here now in more specific format. So what we do in general is this, guys. If there is in question, we call this distance from here to here x. We put our load there. So this is our load. And the load is 100 pounds per foot. Okay? Now, what should I put here as far as my shear is concerned and as far as my moment concerned? I have 2 options here. Either to put it this way or that way. Everybody understand? This one or that one? This one or that one? Which one should I put there? Now, I want to go back again to static. In a static, we said everything that it is unknown, we are going to put it in positive. Remember that? So the answer comes positive, means that direction is correct. If you put it in the negative, this is the problem. If you don't have a unknown forces somewhere, you put this in the negative direction, and the answer comes positive, means it is negative. Is that correct or not? Yes? Which one should I choose? Should I choose this one, or should I choose that one? Which one is positive? Which one? This one. Everybody. And this is, so go to your sign convention and put this. This is a positive M, but look at here. Which one is positive shear? It's not this one. The positive shear is that one. Yes or no? So you always write it down. You always, when you draw free body diagram, you choose those stars, and you put it here because you don't know what's going to end up. Then we are going to assume it is a positive m here. Okay, this is a positive m and positive shear, and we are going to call it mx and vx as a function of x because it's going to change with the x. Is that correct or not? Yes? Then we are going to apply our static equilibrium to it. Now look this again. I have assumed, I don't care what's happening here. I don't care because this could be much more load here, 10 of them, 100 of them. I have assumed my shears to be positive and my moment to be positive. I have seen even today, ME219, I gave, actually this was last quiz, I gave them one of these simple, much more complex problem. They put the moment here. If they put the moment here, they are already assuming it is in negative format. Everybody and if the answer comes positive, it means negative. Yes, because they draw it in the negative format, correct? Are you getting my point there? You have to draw it with this and this because this is the right-hand side of the cut. This is the right side of the cut. This is the right-hand side of the cut. Is that understood? Yes? Then we go to our sigma fx now and sigma fy. So sigma, now we go back to a static. From here, now we are moving to this direction. So I put it like that. Then sigma fx equal to 0. That's 0 equal to 0. That doesn't give me anything. Sigma fy equal to 0. Remember, in sigma fy, everything here is plus. Everything here is minus. I said that. Now, how much load do you have here? How much load do you have? You have the value of this load is 100 times x. Upward or downward? Downward. Therefore, it is negative. So minus 100x. This one is upward or downward? It is downward. Forget about this. Now we are on a static. A static, everything downward is negative. Everything upward is positive. So minus Vx equal to 0. Vx equal to minus 100x. This is the equation of the shear. We already plotted. Look at that. Already by inspection, we saw negative. Everybody see that? Now, what happened here, if you draw this upward, this comes plus, which is wrong, because originally you are assuming it is negative. Everybody understand what I'm saying? So please, aside from understanding or not, always on the right-hand side, choose these two. Is that understood? That's how you proceed. Correct? Until we practice. Now we come to the moment. Now you have two choices, either to take the moment about A or make the moment about that cut, which was somewhere here. So that cut was here, and this distance was x. Is that x keep changing from 0 to 6? Is that understood? Yes? Correct. Now, if I could do that, sigma m, now where do you want to take? Obviously, you don't want to take moment about A because you want to get rid of that. In order to get rid of that, you have to take the moment about the section. Is that correct? We usually call it sigma m at where x is or where xx, I call it, equal to that. That's where we are. Is that correct or not? Then how much moment this gives me? 100x times this distance. What's that distance? 100x times? Come on, guys. If this is x, what is this? This is x over 2, because this is a rectangular shape. I put the load at the middle of it. You know that from a static. If this is a rectangular shape, you put the load at the middle of the rectangular, which is at the x over 2. Is that correct or not? So it is the moment of that one is 100x. That's the force itself. Multiplied by what? X over 2. Is it plus or minus? This is a static now. Is it counterclockwise or clockwise? It is counterclockwise. Therefore, it is plus. This is we are using here. This is a static, guys. This is back to normal. This is here. So forget about that. That is only for plotting shear and moment diagram. Now I'm using a static as you always used it. Everybody, and I always used it. That depends on your sign. Here plus, here plus, here plus. Is that correct? I put it here. Everybody see that? So I'm using that way. This moment is plus, correct? Plus what? Plus this one, because that's a couple sitting in the positive format. Is that correct or not? Correct? Plus mx equal to 0. That was your mistake. You were putting mx equal to that. Wrong. This action plus this reaction together must be equal to 0. That's what the equilibrium is about. Many people stood. She did. Went ahead, Go to chapter 5, try to do this, but she was using mx equal to that. Wrong. It has to be action plus reaction equal to 0. Everybody understand that? You know that. You have mentioned it that. So mx become what? Mx become, look, opposite to that. Minus 100x over 2, which is a parabola. Therefore, my moment diagram starts here at 0, and it goes to a parabola. Where is the maximum m? Where is when x equal to the highest value, the x become equal to 6. Everybody understand what I'm saying? That, which is exactly your moment at that time. You can calculate that. At this moment m, here mb become equal to minus 100 times 6 to the power of 2 over 2, which is 36 divided to 1800. Minus 1800 pound-foot of motor. So this beam still is going to break here, but it's going to break because now if you are going to chapter 4, how much moment do you have there? 1800 of pound-foot, yes or no? Correct? And it is a negative moment. That means tension on the top, compression on the bottom, because that's the negative moment. Tension on the top, compression. Everything fits. Is that correct or not? Now, one more. Okay, we have done all of that. So one more, and then we decide on something very important. So the last one, or the one before last, is this one. So if you do all of that, you should be able to do all your homework. Here, I'm going to put here a force of 900 pounds. And I'm going to call this 2 feet and 4 feet, like that. This is totally different now. Okay? Correct? All you have to follow is the rule of the sign, which is for drawing shear and moment diagram. By the way, one I'm repeating myself. When you go up to the static, you go back to the static format, which has nothing to do with this. Is that under? These two are separate. This is just for plotting purposes. Now I know this is a negative shear. This is the negative moment. Everybody understand that? That means if I cut the beam here, I can calculate the moment at any part. But here you lose maximum. Here maximum. Does that happen to be negative? And this is negative. All of them. Now here is different. First, I have to calculate the reaction. This is very simple. Everybody understand? This is the ratio of 1 to 2. So here I get 600 pounds, and here I get 300 pounds. This is part A. Everybody can do that by using moment or ratio or whatever. Is that correct or not? Yes? Shear diagram, guys. The shear diagram. Now I need 3 points. This is X. This is point A. This is point B. This is point C. So you bring A down. You bring B down. You bring C down. Now, what's the shear value at A? Now, you have to be a little bit more quick. What's the shear value at A? An epsilon after A, in other words. 600, correct or not? Is it plus or minus? Everybody should have an answer there. If you have not answered, then you know that you are not looking at the sign convention correctly. The force is up, shear is down. Which one is it? Is it this one or this is this one? Force up, shear is down. Which one is it? It is plus. Yes, so I must start with plus 600. Yes or no? It's the reverse of that one, guy. If this was negative, this one was positive. I mean, so this is. Are you okay? Did you get it? I put a little cut here. This is up. This is down. Look at it. The sign convention. You have to learn that. That sign convention, you don't need. That's the only thing you have to remember. I'm fortunate. This is the one that eventually everybody we're going to learn it. Is that correct or not? You have to learn the sign conversion. That's not something I can give it to you. So therefore, since this is that format, this is up, this is down, therefore start from 600. Yes or no? Then as I go forward, is it changing? No. Up till this point. So therefore, go to an epsilon. You have to, by the way, like before, if you go to the B, it is ambiguous. There is no answer there. You should stay at epsilon before or epsilon after. Everybody understand? This is the problem we had in the earlier problem. I put several load, and then you were trying to calculate the internal force. Remember that? I said, do not go to the point. Go in between. Is that correct or not? This is the same thing. Before point B, the shear is 600. After point B, is it the shear going to change or not? Just answer me that. It's going to change. That's the whole point. How much is going to change? By 900. But should I go up or should I go down? Now, because force is 900 is down. If 900 is down, it gives me this one, which is negative. Therefore, I should be going down, not up. Everybody see what I'm talking about? Therefore, at plus 600, as soon as I pass there, I should be going down how much? 900. So I end up with minus 300. It goes like that, goes up 300. We are back. So this part of a shear is plus. That part of a shear is minus. Guys, look at it. Is it going to bend like that? Yes or no? Correct? This shear is positive. This shear is negative. Look at your sign convention. Yes or no? Correct? Matching here, correct? This shear is plus, this shear is minus. Do you see what I'm talking about? Okay. Now how about the moment diagram? Okay. So the moment diagram, all right. If 600 times 0 is 0, yes? Then 600 times 1 foot become 600 times 2 feet become 1200. This is a static, guys. As you go forward, 600 times a distance of 2, how much is the moment? The moment is 1200, yes or no? Internal moment, yes or no? But is it plus or is it minus? Plus, yes or no? Because you saw the spending like that, you don't have to go any further. Is that correct or not? But there is another relationship I'll give you in a minute. So, by the way, it goes up to this point, goes to plus 1200. This is M. Then at this point, should end up back to 0. So I'm going to tell you this is going to end up 0 here. I'm going to explain that in a minute. So therefore, don't worry. But before I do anything, I'm going to erase this part. This is a static sign convention. One review, guys. This is static sign convention. This is sign convention for moment and shear diagram. This is how we use our free body diagram. Now, do you see a pattern there? Did you notice that in this 3 problem, there is I'm creating shear and moment diagram, but I'm going to explain one more time. Don't look at this point and that point and that point. You should always remember, this is what I'm going to put here, a blue marker. Where is my blue marker? I lost it. I use it for other class. I should have it here. Oh, here. Okay, you should be here, 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 etc. Now, from here to here, do you have any load? No. Forget about this. Is there any load here? No. Look at the shear. The shear is constant. The moment is linear. Look at here. From here to here, shear is 0. Moment, sorry, I forgot. The load is 0. Shear is constant. Moment is linear. Look at here. The load is constant. The shear is, the moment is a parabola. Is this a pattern? One is integral of the other one. So that is the one is going to help you the most. Everybody understand that. One is, what's the integral of a 0 is a constant, yes or no? What's the integral of a constant? Is cx or whatever. What's the integral of a cx? Is cx squared over 2. Look what we got here. Yes or no? Therefore, write it down. One is this. So we need this table, which is going to help you. This is it called in chapter 5, 2, or 3. They are calling it the relationship between shear and the load and the moment, which is the integral format. And since you are very good in calculus, I'm assuming all the integration applies here. Everything that you know about the integration applies here. So this problem becomes static base and equilibrium base and static. So next year, it's going to be part of a static. Definitely week 6 or 7 in a static, we are going to teach them how to draw shear and moment diagram, because it has nothing to do with the stresses yet. Everybody understands it. It has nothing to do with the strength of material. It's base static. Now, I want you to draw this table and look at it. And then in the handout, if you have color, if you have printed in color, I will show that later on, that how I gave you all this information in your handout, including the sign convention. Put here W, or the load here. Put here shear. And put here M, or moment. What we are saying is this. If this load is 0, as you saw it in several places, the last example and the middle example, when the load is 0, the shear was a constant. Now, it could be plus or could be minus. I'm not deciding that. That you will decide on that. But the moment will be what? The moment will be linear. Again, plus or minus. Applies here. Look at it, guys. 0, constant, linear. Is that correct or not? Yes? And then if the load become, second example I did, a load itself become a constant. Notice that was a constant of 100 pounds per foot. Yes? What the shear was looking like? What's the integral of a constant? Look, 100, this become 100x, this become 100 x squared over 2. Everybody see what I'm talking about. Therefore, the shear is become a linear, and the moment become a parabola of x2. Is that correct or not? And this can go on and on that. Previously, last year, I gave the student also a load like this, which itself is a function of x, because linear, you can call it kx. Is that correct or not? Yes? Come on, guys, don't look at me surprised. I mean, this is very elementary. A line representing a load is not 100 pounds, or it keeps changing. It is kx. Is that correct or not? This is the equation of a line going through the center of coordinate. Slope times the x. Is that correct or not? Okay, so therefore, that's then the moment become, so this is become function of x. Is that correct? So in other words, this is x, this is x squared. Is that a parabola means x squared, first parabola. This is constant, x squared. 0, constant, x. This is what we just go one up. And here, of course, the shear will be what? Shear will be a x squared, and the moment will be x to the power of, it's a parabola. And this can go on and on. What do you think you have here a Boeing 707? What do you think the load on the wing of an airplane is? This is a parabola of certain order. Is that correct or not? So this can go on and on. We never go in this class. I did not give you any example at this time. I cut it out, actually. It was part of that number 11 and 12. I cut it out because of shortage of time. I don't have to explain it to you. It can be done. It's very simple. However, if you go here to like a load like that, which is a function of x is given to you, if this has x to the power of n, this become n x to the, by integration method, this become x to the power of n plus 1, and this one become x to the power of n plus 2. We call this relationship. It is in your handout. Take a look at it. So that those graphs that you see in your handout, take a look at your handout. You should print it in color. So you see it in color, some of them. There are a couple of pages from different books. Is that understood? You see that? They show you how this changes, plus or minus. We talk about detail of it later on. How much time do I have? Do I have a couple of more minutes, 4 minutes? Okay, good. I can do another example. Everybody see what I'm talking about? Yes? Okay, so one more example of that sort, which you will see the same. So really what is key here is this 3 item here. Static, remain static. One more time. No changes there. You have to choose this format and this format in order to assume your moment and shear are in positive. No, for equilibrium, you choose it that way. We are assuming positive. Notice if you put at this end this way, you are already assuming it is in negative. And that's not the way we do it. When everything is unknown, we put it in positive diagram. You know that from a static. Everybody understand that. So we choose, whenever you do a cross section, we do that. For this simple problem, I did not use the free body diagram. For next problem, which is a little bit more complex, I have to draw free body diagram at certain point and then put the points together. All I'm saying that if this problem becomes a little bit more complex, you cut it at certain distances and you draw your free body. I'm just giving you advance notice in case you want to work between now and Thursday. But of course, you have to worry about chapter 4 as well. Is that understood? So therefore, one more problem doesn't hurt. Where should I erase? Here. So, okay, I do the fourth problem here, which is similar to what you just did there. That one, but this time I'm going to choose a beam like this and put a uniform rod. Notice that one was a cantilever beam. This one is 100 pounds per foot. It is 6 feet. And a pin here, a roller there. This was free, this was fixed, everybody said. Already you know how it should look like because I already gave you the table. Look, this is, the load is constant. Shear should be linear. Moment should be a parabola. The sign is obvious. Look, guys, look at it. You see, everything is there without you to look at it. Is the beam is going to bend like that? Because the load is downward, yes or no? A uniform load, the weight of that, because of the weight of the beam, is going to go like that. So is it a smiley face? Yes, so the moment should be. But look at the shear. This side shear is. This side shear is. So what's the problem with that? We should already be plotting that quickly. So what's the reaction here? Come on, guys. The reaction here is symmetrical. So 100 times 6 is 600. Divided by 2 is 300. This should not take more than a minute to do it. Is that correct or not? Yes? So the shear diagram. Shear versus, X versus shear in pound. What's the value of the shear there? See, what's the value of shear? You already have done 300. This is going up. Shear is going down, therefore it is plus, yes or no? Plus 300. Look how simple it is. Now, how much am I reducing it? I'm reducing it by, because this is by the rate of 100 per foot. Everybody, and so if I go 100, I have to reduce it by 100. I go 1 foot, 100, 2 feet, 200. But you don't have to worry about. When you go to this point, how much should you subtract that? This is 600 at the rate, but it's linear. It's not it's straight. It should be linearly going like that, and it should end up with minus 300. Where is shear? 0 at the middle. Is that correct or not? So therefore, this is plus 300. This is 0. By the way, when shear is 0, what happens to the moment? Isn't this the integration, guys? If this is the integration, by the way, I want you to, if you go this way, you integrate. I give you the load in future. When things come a little complex, you can integrate to get the shear. You can integrate to get the moment. This way will be what? This will be the d by dx. If I give you the moment, you can differentiate to get the shear, and you get differential to get the force, the load. Is that correct? This relation, actually, you're going downward, this is integration, you are coming back, it will be the differentiation. Is that understood as far as the math part of it is concerned? Correct? Now, we are coming here. How do you find the highest value of a function in the calculus? What do you do? If I give you a function fx, how do you find the peak? You take the derivative, you put the derivative equal to 0. What's the derivative of m? What's the derivative of m is shear. So if shear goes to 0, m is, that point actually is most valuable point there. Everybody understand what I'm saying? That the one, this is integral of that one, moment is integral of that one. So if I take the derivative of moment, it becomes shear. So if the shear goes to 0, m must be what? S must be the highest value. You draw what I just did that. You draw that parabola. The parabola becomes like that, and this is the highest one. Again, constant, linear, parabola. This is plus, this is minus. Look at it. But the moment of everything is plus. What's the highest value of moment? At the middle. The idea was finding m max and shear max. For every problem, we did that. This is m max. This is shear max. This is shear max. This is m max. Is that correct? And so on, so on. So if you look at every problem, I end up with the highest value of the shear. So next time, Thursday, before the quiz, I'm going to do a series of more complex problem, and that's the end of it. So next week or over the weekend, you have to work on this one. But don't forget about your sign convention. Okay, good.